Hello everyone, this is a follow-up discussion on the previous lessons on electron configuration. So by now you already know how to write the electron configuration of an atom based on the period by looking at the periodic table. Now some of you might have noticed that there are some discrepancies in what is expected and in what is an actual electron configuration. So I appreciate those who really took time to look up if their answer is correct or not. Okay, so that's one good way of studying. Now, you might have noticed that in the D block, okay, this is where things start to get a little bit tricky and confusing for a while. Okay, so if you look at the fourth column of the D block, it says here, for example, chromium 4s1 3d5. Okay, but we know very well that it should have been 4s2 3d4, right? Okay, and the same thing happened with molybdenum, that 5s1 4d5, but it's still in the fourth cell. So what happened to why is there an additional electron to the D sublevel and there is lacking already in the S? All right. So same thing with the ninth column of the periodic table. We're starting with copper, followed by silver, gold. So instead of having 4s2 3d10, then all we have is 4s1, 4s2 3d9. We have 4s1 3d10. So what could have happened? Now you might have noticed that there are other elements that are, in a way, exceptions to the rule, to the off-bow principle. And then here is a list of those elements, and I've already written down beforehand before recording so that it will not lag. But anyway, so the question is why? Why are they exempted? What could have happened to the atomic orbitals of these elements? So common ones are copper. Okay, so you have copper, silver, gold, and then you can also add chromium here, right? So Cr is also one element present, right? But it's taking time, so let's go. So here is an annotated version already of the slide presented. So here we have the predicted electron configuration and the actual configuration. Okay, so as I said, there are some electron configurations which we may not understand and or what could have happened to that one electron. Okay, so let's take for example copper in here. Okay, so if we are going to draw the orbital diagram of copper, in our expected electron configuration, we have 2 electrons in the 4s and 9 electrons in the 3d. However, this isn't the case because there is one electron here that is lacking, and in order to make copper a stable atom, then it has to transfer. Okay, they found out that a full or filled 3D orbital is more stable compared if there is an incomplete set, right? And then how do they know this? They actually observe the properties of copper compounds, say the way it interacted with certain atoms, and they deduce this kind of information. Otherwise, they also have some advanced analytical techniques like X-ray crystallography to posit how it is that uh, a filled, okay, 3D orbital is actually more stable. Okay, so that is what happens for copper. One electron from the 4s, okay, transfers actually to the 3D, making it 3d10 and leaving this as is for S1. Okay, and in this version, this electron configuration has lesser energy. Okay, has lesser energy. That means it is more stable. Okay, in chemistry, we usually think of lesser energies as the one that is this more stable. Okay, and then another example is chromium. Okay, chromium in the same manner as copper is listed as has an electron configuration of 4s2 3d5, 4s2 3d4. But here we in the actual electron configuration we have 4s1 3d5. So what happens here is in order to at least complete the sublevel halfway, then one of the 4s electrons must have transferred. Okay, so they found out that half-filled d orbitals are more stable compared to those that have lacking electrons here. So the conclusion was a half-filled and completely filled d orbitals are more stable and have lesser energy. Okay, and why is that? So I hope this example is clear. The same thing with the rest of the examples. Okay, so what happens to one of the electrons of the 5s, and why did it why did it become 10 here? Okay, by the way, this table or this chart lists the terms of the electron configuration from lowest to highest number, which is also fine. Okay, but in we are also used to doing the uh, traveling through the periodic table. That's why we started with S here. Okay, but this is also correct. Okay, so same thing happens with the rest of the elements. Or look at even palladium. So it's actually the two 5s electrons of palladium which transfer to the 4d just to complete the uh, d orbital. Okay, and as we go down the bigger elements in the periodic table, the more complicated the occupancy of electrons are in the orbitals, in the specific orbitals. Okay, it gets uh, more confusing when we go to the F. Okay, but let's reserve that one for another time later. It's actually a big unit. The transition metals, the rare earth metals, they actually can have special characteristics because some of their electrons occupy the D and the F sublevel. That makes them able to form complexes, transition metal complexes, and etc. All right. So I like also to show, okay, how it is that the electrons are able to jump from those orbitals. Okay, so if this is the actual depiction, but this is roughly a sketch, but close enough. Uh, the 4s and the 3D actually have very little energy differences as compared to the 1s and the 2s, okay, or the 2s and the 2p. So you might have noticed that the farther the energy levels are, okay, the closer they become to they are with each other. Okay, whereas for some sub levels, they become closer in terms of energy difference with each other. So it's almost similar energies between the what 4s and the 3D or 5s and the 4D. So that means they can also that is what makes the electrons possible to jump from one thing to another. All right. And then in terms of valency, so we are very familiar with the concept of valency. These are the electrons. When we say valence electrons, these are found in the outermost shell or at the highest energy level. Okay, and they are the ones that participate in chemical bonding. And for group A elements, it is indicated by the group number present. Okay, but you can also deduce the number of valence electrons from the electron configuration by looking at the terms with the highest coefficients and adding the number of electrons so that you can get the valence electrons. Okay, and this is the video shown. So this is not mine, it was downloaded from YouTube. Thank you very much for this uh, educational resource. Okay, and then let's just play it so that it can be used as a good reference for study also. All right, the links are also in our teams if you want to have a clearer picture.
You might not think of water as being magnetic, but it is, and so are graphite, aluminum, and glass. This is a new and different category of magnetism called either para or diamagnetism, and it's different from the magnetism that you're used to. You're probably already familiar with ferromagnetism. Ferro means iron. An unmagnetized piece of iron, or nickel or cobalt, becomes a magnet in the presence of a magnetic field. The effect is strong and lasts even after the magnet is removed. Paramagnetism is a similar effect, except that it's much weaker and temporary. Aluminum is a good example of a paramagnet. And so is oxygen, which is attracted to magnets. Here, I have a few milliliters of liquid oxygen, which sticks to the magnet. I'll explain why later. Gadolinium oxide and cupric sulfate are good examples of paramagnetic substances. Cupric sulfate is a salt that can be picked up by a magnet. Diamagnetic materials are exactly the opposite of paramagnetic. They are always repulsed. They would rather die than be in a magnetic field. An important example of a diamagnetic material is graphite. This specially made pyrolytic graphite is repelled by a magnetic field. Don't be confused. This is not static electricity or eddy currents. Graphite is repelled by a magnet, always, both by the north and south end. Pyrolytic graphite is a grown crystal of flat carbon layers which maximizes the diamagnetic effect. Of course, the best diamagnets are superconductors, which at low temperatures provide exact opposite repulsion to whatever magnetic field is present when they're chilled. They are perfect diamagnets. The most famous and powerful diamagnetic is bismuth, element number 83 on the periodic table. The bismuth-powered boat sails toward the weaker magnetic fields. One way to check whether an object is diamagnetic or paramagnetic is to see how it aligns itself in a magnetic field. Diamagnetic objects like glass will rotate to avoid magnets. Here, we see that the glass is diamagnetic because it twists to get to the weaker magnetic field. But aluminum rotates into the field, typical of a parallel paramagnet. On the periodic table, we see that aluminum has 3 valence electrons. So what does it take to understand what it means for something to be a paramagnet or a diamagnet? You have to know what the electrons are doing. Consider, for example, aluminum. We see from the periodic table that aluminum has 3 valence electrons. That's 2s and 1p. Now it's that unpaired electron that makes it a paramagnet. This unpaired electron enables it to become magnetized. And it's that unpaired electron that is free to be magnetized and attracted by the magnet. But what about a diamagnet, like water? Yes, the water molecule. It has all of its electrons paired. It will not be magnetized. In fact, water is repelled by a magnetic field. The electrons come to lower energy as they are moved away from the magnet. In conclusion, when something is a paramagnet or a diamagnet, it tells you what its electrons are doing. In the case of a paramagnet, it has at least one unpaired electron. In the case of a diamagnet, it has mostly paired electrons.
Okay, thank you very much. So, summary for the discussion a while ago, there are 2 types of magnetism exhibited by elements or atoms. So you have diamagnetism and paramagnetism. So the key here is we just draw the orbital diagrams, even if we just draw the outermost part, okay, or the last terms in the electron configuration. So as long as we see that there is at least one unpaired electron, we consider that atom to be paramagnetic, meaning to say it is attracted to an external magnetic field. Whereas if all electrons are paired up, then that means it is very weakly repelled by a magnetic field, and the type of atom is diamagnetic. And you see here what happens to the spin alignment with the magnetic field B. So in physics, we usually represent a magnetic field as B. So for diamagnetic, it is anti-parallel, okay? It stays away, or it is repelled, while for paramagnetic, it aligns with the magnetic field B. All right, and then you see here how the what the effects of those electrons are on the magnetic field lines. All right, so one thing that is very notable is uh, those with odd number of electrons, the total number of electrons is odd, then mostly they fall under paramagnetic. Okay, because in diamagnetic, everything has to be paired up, man. So if it's odd, then there is at least one electron that has not been paired up. So that makes it paramagnetic. But if the total number of electrons is even, then it could either be paramagnetic or diamagnetic. Okay, it depends on the placement of the electrons in the orbital. So you really have to draw the orbital diagrams. Okay, again, for if you just look at the number of the total number of electrons, if it's odd, then automatically we consider that atom to be paramagnetic, while if it's even, the total number of electrons is even, it could either be paramagnetic or diamagnetic, depending on whether there is pairing on the orbital diagram. If there is one electron that has not been paired, then that's paramagnetic. Okay, so some simple mnemonic, okay, that I just looked up to, and this also not mine, but yeah, I think it works. If it's unpaired, it's attracted. So that's paramagnetic. Okay, and the other one, if it's repelled, then that's diamagnetic, and all electrons are being paired. Okay, so for example, you have here lithium. So we see that lithium has one unpaired, so this is paramagnetic. Beryllium is diamagnetic. Boron is paramagnetic. Carbon is paramagnetic. Nitrogen is paramagnetic. Okay, and then neon is the small e, by the way. Neon is diamagnetic. Okay, I think the only ones here that are diamagnetic are beryllium and neon. Again, diamagnetic, all electrons are paired up. All right. So that's it for diamagnetism and paramagnetism. Now, I'd like you to look at this video as it sums up our discussion on the quantum mechanical model. Okay, this talks about not only the applications of the quantum mechanical models, but also the implications. Okay, where we are headed now that we know these things. And I'd like you to think about the nature of science, the nature of chemistry as we go about these applications. Again, this video is not mine. It is also from someone from YouTube, and then I'm just using this as a rich source of material, a very understandable one. Right?
Hello, I'm Simon Whistler. You're watching Top 10 called subatomic particles. However, much of the discipline is still a mystery, even among the most experienced of physicists, with many calling it a weird science. In any event, here are 10 of the most revolutionary implications of quantum physics. Number 10. Nuclear fusion power plants. Nuclear fusion in the sun is actually the reason why life exists on Earth, and also the reason why Mercury is basically just a lifeless roasted rock. The abundance of hydrogen atoms in the sun, along with the heat and pressure, ensures their constant fusion into helium atoms, emitting radioactive energy in the process, which comes to Earth in the form of sunlight. Quantum tunneling is among the fundamental processes with which fusion occurs in the form of chain reactions. Scientists and governments are currently trying to mimic this process on Earth, for which the services of physicists and engineers with advanced knowledge of quantum physics are being employed. Although the dream of powering the electricity grids with nuclear fusion remains just a dream, scientists expect that new breakthroughs in the understanding of quantum mechanics will bring that dream ever closer. Number 9. Perfect timekeeping.
Whether it's about sinking several space stations and satellites circling the planet, or getting a perfect time reading from the Mariana Trench on Mount Everest, atomic clocks utilizing the principles of quantum mechanics are already making enormous contributions to humanity. However, with the demand for greater accuracy increasing, more advanced quantum clocks are expected to be extremely crucial in helping to meet these goals. So, from ultra-precise self-driving cars to space travel, the principles of quantum mechanics will be extremely important in setting the pace for the future of humanity. Number 8. Extreme computing. While computing technologies have come a long way in the last century, artificial intelligence is only just beginning to catch up to the abilities of the human brain. Today's silicon-based computer chips are soon expected to be insufficient in handling the demands of the future, where machines and humans are expected to be interconnected in a vast network that will be several times larger than today's overall internet infrastructure. In this regard, quantum computing is currently being identified as the prime technology to replace the current one. The technology basically manipulates the natural properties of the atom to store and process data in real time. In fact, experimental models of quantum computers have already yielded enthusiastic results, although scaling the same to economically feasible units has proven to be rather challenging. However, scientists expect that the technology could start dominating the global landscape by as soon as 2030. With the new technology, data processing abilities are expected to make such leaps that calculations that take current supercomputers over 2 years may be completed by quantum computers in just a few seconds. Number 7. Intergalactic travel. Humans are still a long way away from establishing habitable outposts on other planetary bodies. However, if you believe the words of futurists, our hopes of conquering the final frontier will depend a lot on our knowledge of quantum mechanics. While conventional technologies may not be able to deliver enough speed for humans to even colonize other planets in the solar system, astronomers and space travel enthusiasts frequently are very hopeful about the possibilities offered by quantum physics. The spaceships of today already use quantum clocks, while the use of quantum computers is expected to bring humans even closer to perfecting future spaceships. Experts believe that a better understanding of quantum entanglement will ultimately be the key in perfecting intergalactic travel through wormholes. Number 6. Extremely secure cryptography. With hacking and online security identified as one of the most pressing concerns of this century, the demand for more secure cryptography is high. From banking transactions to personal messages, billions of exchanges of data every minute are supposed to be kept secure. But this has proven to be something that's not very achievable with existing technologies. It is here that quantum cryptography has been identified as the silver bullet against online security threats. Basically, the technology manipulates photons to store and share information on a subatomic level. In fact, the technology has already been successfully applied in several instances, like voting and satellite data. Many technology companies are already spending their resources on quantum cryptography in order to scale it and make it more accessible for the technologies of the future. Number 5. Incredibly detailed optic devices. Today, one of the most widespread applications of quantum mechanics is happening in the field of optics. The most advanced microscopes in the world today apply quantum tunneling in identifying the smallest objects like DNA and electrons. In fact, most of the modern microscopic innovations and discoveries owe their existence in some way to quantum mechanics. In the future, the most accurate telescopes are expected to make use of advanced quantum principles as well. Number 4. Tackling diseases and ailments in the human body. Over the years, the principles of quantum mechanics have played a major role in the development of modern radiography machines and MRI scanners. In the near future, innovative technologies developed with the application of quantum mechanics are set to bring even more massive changes to healthcare. Experts have identified nanotechnology and quantum computing technologies as the tools that will help deal with threats like cancers and organ failures more effectively in the future. Reliable researchers have also pointed out that these technologies will also help the human body fight more effectively against other diseases in the future. Number 3. Finding evidence of parallel universes and the multiverse. The concept of parallel universes has been one of the most fascinating subjects for fans of science fiction. Indeed, the concept is still broadly considered to be a theory rather than a fact. While physicists and astronomers in general are divided over the existence of parallel universes, many well-known scientists have stood behind the concept. On one occasion, Stephen Hawking theorized that black holes could in fact be portals to another universe. Meanwhile, renowned scientist Brian Greene believes that the concepts laid out by string theory can point out the fact that parallel universes or multiverses can indeed exist. Scientists like Hawking and Greene have pointed out that with a better understanding of quantum mechanics and with much more advanced tools in the future, we may indeed discover sooner or later that the universe isn't so lonely after all. Number 2. Shatter our concept of time and space. If Einstein's theory was already too complex for you, then modern physicists are probably going to confuse you even more. Firstly, for the definition of space, modern scientists are of the consensus that the seemingly empty part of the universe isn't actually empty at all. These supposedly empty parts of space contain something that scientists call dark matter and dark energy. These two things together are estimated to make up around 95% of the entire universe. On the other hand, modern physicists also consider time to be something of an illusion. In fact, the very concept of any event as a past, present, or future occurrence is refuted, with the principle being that reality is timeless. Moreover, the same scientists also entertain the idea that the linear concept of time is incompatible with quantum scale. So basically, if we believe the words of quantum mechanics enthusiasts, what we thought was empty isn't actually empty, for example space, and what we thought was an undisputed reality doesn't actually exist, i.e. time. Number one, consciousness makes reality. What if reality is the result of an accumulative consciousness? Or what if reality didn't create you, but in fact you created reality? Of late, the term that incites the most vigorous debates in the world of theoretical physics is consciousness. While there is a basic consensus among theoretical physicists that the state of matter at the quantum level can differ to an extent, depending on the interpretation towards it, some scientists, like Robert Lanza, Roger Penrose, and Stuart Hamroff, have gone a step further and theorized that consciousness actually defines how matter actually acts at the quantum level. Lanza, for instance, considers that time and space are mere tools that are applied by the mind to interpret information of the universe. Hammeroff and Penrose have, on the other hand, theorized that consciousness is actually the consequence of quantum gravity effects in vibrating microtubules that are present in the neurons. Hence, if you would want to believe academics proposing these notions, you are right now creating reality and living in it, like spiders creating their own webs to catch themselves in. So I really hope you liked that video. Hopefully it bent your mind just a little bit. If you did, please do hit that thumbs up button below, and don't forget to... Hello, I'm Simon.
Okay, so that's it. So a lot of applications and implications from the quantum mechanical model. It's a very small thing. We can not even see it with our naked eyes, but there are so many applications that help us understand nature, understand the cosmos, and understand our realities, and most of all, understand ourselves. So we stay curious as ever, because the more discoveries there are, the more questions will arise, and hopefully you will be one of those people who will be able to answer those questions. So that's it for today. Thank you very much.